Hello everyone. My name is Thomas Thierauf and this is joint work with Pranjal Dutta and Nitin Saxena. We show that lower bounds for sum of square representation of polynomials imply lower bounds for circuits. Let us start with sum of square representation. So given a polynomial over some field, polynomial is here univariate. And then a sum of square representation is a formula like this, where you have polynomials and sum the squares. In mathematics, this would be called a weighted sum of square representation because we allow these coefficient Ci elements from the field. This has a long history. There is famously Largish four-square theorem that states that every natural number can be written as a sum of four squares. With respect to polynomials, there is Hilbert's 17th problem. That's slightly different. So here he considered multivariate polynomials, first of all, and only positive ones. So there these coefficients were not allowed. They are fixed to be 1. And the FIs were allowed to be rationals. And the question was which polynomials can be represented that way. And such as sum of square conditions appear as conditions in convex optimization and control theory. First of all, we introduce a complexity measure for sum of square representation, and for this we consider the sparsity of these FIs here. So the sparsity of a FI is just the number of monomials it has, or in other words, the number of non-zero coefficients. And then the size of f in this formula here is just the sum of the sparsity of the FIs. And the minimal way you can write f that way, this is the support sum of f, abbreviated by S of f. So in our setting, every polynomial has such an, can be written that way, that you can see from this trivial formula. Every f you can write like this. And that means when you look at our complexity measure, this formula gives you an upper bound. The sparsity here is the sparsity of f, maybe plus 1, because we have a constant term here, again here. So this gives you 2 times the sparsity of f. The plus 2 is for the constant terms. And so this is an upper bound for support sum. And we also have a lower bound of square root the sparsity of f. This is simply by counting monomials, because you square, you need at least square root many monomials as f has. In the examples we consider, we usually have the case that the sparsity is d plus 1, which means it's full sparsity. Every coefficient is non-zero. And then you can translate this bounds here into square root d as a lower bound and 2d plus 2 as an upper bound. Let us look at 2 examples. So here's a polynomial, simply sum of x to the k. And now you can verify that we can write it in this way as a product of 2 polynomials. So here you see a prefix of this polynomial, just the same sum, but only up to square root d. And when you multiply it with this polynomial, then you can verify that you actually get f. And observe that this bracket has square root d terms, and same for this has square root d terms. So let's call these two brackets u and v. So this is then u times v, what we have here. And now you can verify that this expression here gives you u times v. And this is a sum of square representation we get. And so we can conclude that the sparsity of one term plus u plus v or u minus v has sparsity 2 times square root d, and therefore support sum of f is bounded by 4 square root d. So remember the lower bound from before, that was square root d, so that means we are essentially at the lower bound, except for the constant factor. A second example is this simple function x plus 1 to the d. So suppose this d is even, then you can write it that way. And this is a sum of square representation with just one summand. And this shows that support sum is bounded by d by 2. When d is odd, you get a slightly larger support sum that way. So here we are more close to the upper bound for support sum. And yeah, conjecture in this case is that actually this is the true value, and we will see that if one can prove this conjecture here, that would have big consequences. So we connected with algebraic circuits. So here you can see an example of an algebraic circuit. It's defined in the obvious way. It defines a polynomial. Gates are plus and multiplication gates, and it's also allowed to put constants on the wires here, and then it computes a polynomial in the obvious way. The size of the circuit is a number of gates and wires, and there's also a notion of depth. Complexity classes defined based on these circuits are defined by Valiant. So VP is all polynomial families that can be computed by polynomial size circuits. It somehow is the analog of the Boolean class P, polynomial time. And similar, VNP is the arithmetic analog of Boolean class NP. It's defined as exponential sums of VP functions. And what is called Valiant's hypothesis is that the permanent function is not in VP. It requires superpolynomial size circuits. This is equivalently to say that VP is different from VNP. And this is the big open problem here in the field, similar to the P different from NP question. Okay, yeah, we need the notion of an explicit function. An explicit function roughly is a function, a polynomial where the coefficients are easily computable. So suppose we have a family of polynomials, fd of degree d, and then we look at the coefficient function that gets as input JID, and the output is one bit, namely the jth bit of the coefficient of x to the I. And then we say this family is explicit if the following two conditions hold, namely all the coefficients have to be polynomially bounded in the degree, and the coefficient function has to be efficiently computable in P. Actually, one can relax this, and it suffices for our purpose that it's in Sharpie/poly. So these are the examples that you can easily verify fulfill this property. An example that is not explicit is this function here. And the reason is that these coefficients are just too large. The double exponential would violate these conditions. Okay. So now we define a notion of sum of square hardness. And I defined explicit before because we restrict this to explicit families of polynomials. So we say such a function is SOS hard if the support sum size is larger than square root d plus its epsilon and the exponent. So recall that square root d was the lower bound. So that means we are just an epsilon away from the lower bound. So in this sense, this is a very mild hardness definition what we have here. And actually we can weaken it for our purpose. I wrote here a constant epsilon just for simplicity, but actually it suffices. Epsilon can be a function in D and it can be decreasing. It should just be larger than this decreasing function. And that's good enough to prove the following theorem. So we show actually that when there exists such a family that is hard in this sense, then this separates VP from VNP. And this looks a bit surprising because I mean what we want is just seems to be a trivially larger than the lower bound we have. So it seems as this should be achievable to show. Yeah, the difference here between the two epsilons is in a way that if we go for the constant epsilon, which is a stronger requirement here, then we can actually prove that there's an exponential separation between VP and VNP, and this is a different proof than the one we show for this epsilon. I mean, it goes along similar lines, but uses different estimates, and we get a stronger separation. There's a paper by Rubisch, Victus, and Thierauf, also about sum of square representation, and they show that a lower bound here shows also exponential lower bounds for the permanent, but in the non-commutative setting. So this is a different setting, and also the sum of square representation they consider is slightly different from what we do here. They have a different complexity measure. So this is not really comparable with what we do here. So I show you how we argue to get theorem 1, and the main tool is this lemma here, which is a sum of square decomposition of an polynomial f that is given by a circuit of size s. F has degree d, and here we start with an n-variate polynomial. So now we are multivariate, and the claim is that there exist polynomials fi and constants ci such that we can write f that way here as a sum of squares, and the number of summons is bounded by this expression here, and very importantly, the degree of the FIs is bounded by d by 2, which is half the degree of f. So let me give the main steps of how we argue to prove that lemma. So we start with a given circuit for f, and the first step is to apply the depth reduction to the circuit by these four people. This reduces depth to log d and size d is polynomial in S. Then having a log d depth circuit, we can unfold it and get a formula. And then the formula can be turned again into a branching program. And we want it also to be layered. So here's a lot of techniques going into this, not very difficult. So finally, we end up with a branching program, computing f, and this branching program we can somehow split into half at when there's a start vertex, and halfway we stop and cut all paths, and then we get an intermediate layer, say of t nodes, and each node defines two polynomials from start vertex to the node and from the node to the sink vertex. And this defines two polynomials, gi, hi, and this for every intermediate vertex. And so we get a representation of f in that form here. And because the branching program is layered, both parts have degree at most d by 2. So once you have this, then we are done, because then we can again write f as in a sum of square representation, as we have already seen earlier. So from what we did here, you get an idea why the degree is bounded by d by 2. For the size bound, you have to really go into the construction here, that you can see that this is the S prime we get here. So yeah, these are the crucial steps to get this representation. And now we do it similarly for the proof of theorem 1. I show you the crucial steps again. So we assume we have a polynomial family that has a hard sum of square representation, and this means sum of the sparsities is at least this big. So the crucial thing is to set up parameters right, and this is not trivial. So we choose values n and k that depend on d and epsilon, and this has to be done appropriately. And I will not put the formulas here on the slides, so you can look at the paper, but this is crucial. So what we do is recall that fd is univariate. So we do a substitution and transform fd to polynomials that are multivariate, p and k. They have k times n variables, degree is n, and it's multilinear. And this is a variant, you can say, of the Kronecker substitution. So what we do is we introduce new variables, and then we replace monomial x to the I in fd by a product of the y variables. And this is done such that the variables we take are chosen depending on the base K representation of I. And when you do it that way, you can also reverse the process, because that is an injective function. And so you can go back from P and K to FD by this transformation. I mean, this you have to check. So since we started by assumption with an explicit function FD, one can easily conclude that the polynomials we get here are in V and P. And the main thing we show is that the size of the circuits for P and K is at least this big. And this is super polynomial, as you can see when you look at the paper. And this implies that these polynomials are not in VP. So that separates VP from V and P. Yeah, this goes by contradiction. So we assume these polynomials have small circuits. So first of all, we use the decomposition lemma and write these polynomials in such a way, and degrees of the QIs is bounded by n by 2, half the degree of P. And now we reverse the conversion from before. So this gives you, from the multivariate QI defines univariate Fi, and this equation here translates into the univariate setting. So then this implies a representation of FD as a sum of square representation. And now we can look what is the what gives the sparsity bound here? What is the size? What is the size of FD with respect to this representation? So first of all, this one has to observe that this conversion does not increase the sparsity. So that means sparsity of the Fi's is bounded by the sparsity of the Qi's, and a Qi is a polynomial with k times n variables of degree n by 2. And this is the just the general combinatorial upper bound for the number of monomials such a polynomial can have. So number of variables plus degree, choose degree. This is the trivial upper bound for any such polynomial. So that applies also to Fi's. And so we can conclude that the support sum of FD is bounded by S prime times this binomial coefficient, because the sum is S primes. And we also have bounds on S prime by the decomposition lemma. And now here I hide all the hairy calculations. These are the final estimates we get. So we can actually show that S prime is bounded by d to the small o of epsilon. So that is smaller than epsilon, and this is bounded by d to the half plus epsilon by 2. So when you multiply here, we get this expression, which is same as this. And this is a contradiction, because FD was hard, and this is actually smaller than the hardness assumption we had. So this proves theorem 1 and gives the separation of VP and VNP under a sum of square hardness assumption. Yeah, what is the challenge now to really prove lower bounds for sum of square representation? I can also give you a bunch of candidates where we think they should have support some size around D. And if you can show this, then you would separate VP from VNP. Clearly, there are people who say that, who interpret it in the other way around and say that it just indicates that even this mild hardness thing is hard to prove, but who knows. Another goal could be to weaken the hardness notion we had, to, for example, to something like that the support sum is just faster growing than square root D without the epsilon. And the question is, can we still show that VP is different from VNP? We know that VP different from VNP implies a derandomization for polynomial identity testing. Then you can do polynomial identity testing in sub-exponential time. So this would be also a consequence of the when there are sum of square hard functions. And what we can show is that when we consider sum of cube representation, we get a similar theorem than theorem 1. So we can show that when there exists a sum of cube hard polynomial family, then one can completely derandomize polynomial identity testing. It's in P. But what I hide here is this actually uses a bit a stronger hardness notion than in theorem 1. So here we are quite a bit away from the lower bound. So this is really seems to be a stronger assumption, and we get also a stronger consequence. So it also implies VP different from VNP, but in addition, it completely derandomizes PIT. So this you can find in the paper. Thanks for listening.